there is a number that should not be controversial. A single value that is supposed to tell you right now how fast the universe is stretching. Not in poetry, not in metaphor, in kilometers per second per megaparsec, in mathematics, in predictions that either land on the data or break against it. It is called the Hubble constant, H0, and it is supposed to be one number. If the universe is a coherent story, if space expands according to the rules we believe, then every honest method of measuring H0 should converge like multiple thermometers in the same room agreeing on the temperature. But that is not what is happening. The opposite is happening. As our instruments sharpen, as our analyses get cleaner, as our statistics become almost cruelly precise, the universe does not settle into agreement. It divides. Two measurements, both built on decades of refinements, both performed with obsessive care, both backed by data that has survived every basic attempt at dismissal, are pointing to two different expansion rates. Not slightly different, not different in a way you can wave away as noise, different enough that the gap has a name: Hubble tension. A tension is what you feel before something snaps. And the unsettling part is that it is not tension in our imagination. It is tension in our equations, in our cosmic bookkeeping, in the baseline we use to convert light into distance, distance into speed, speed into the fate of everything. If you have never worried about cosmology before, this is the moment it becomes personal. Because H0 is not just a number about galaxies. It is the conversion rate between time and distance on the largest possible scale. It tells us how old the universe is, how quickly structures formed, how fast emptiness grows. It sets the tempo of cosmic history, the beat that every galaxy has been forced to dance to since the first atoms cooled. If zero is uncertain, then the story is uncertain. And if two precise methods disagree, then either one method is wrong in a subtle way we have not discovered, or our model of the universe is missing something fundamental. That second possibility is where the dread begins. Because our standard cosmological model is not a casual guess. It is a framework that has explained an astonishing amount with a surprisingly small set of ingredients. It says the universe is made mostly of something we cannot see, dark matter, which holds galaxies together like invisible scaffolding, and something even stranger, dark energy, which pushes space itself to expand faster and faster like a silent pressure inside the fabric of reality. The model has a name that sounds almost too sterile for what it claims. ΛCDM. Lambda for dark energy, CDM for cold dark matter, and then a handful of parameters: the density of matter, the density of radiation, the initial seeds of structure, the curvature of space. A recipe, but every recipe depends on measurements, and one of the most important measurements is H0. Here is the problem. When we infer H0 from the early universe, we get one value. When we measure H0 from the late universe, we get another. And they do not want to meet in the middle. Imagine trying to reconstruct a film from two reels. One reel is the opening scene preserved perfectly. The other reel is the ending scene observed directly. You build a plot that should connect them, but when you play it back, the characters are not where they should be. The timing is wrong. The ending does not follow from the beginning. That is the feeling of Hubble tension. To understand why this matters, you need to understand what makes it so hard to measure the expansion of the universe. You cannot stand outside the cosmos with a ruler. You cannot mark the edge and watch it swell. All you can do is look at light. Light that left distant objects long ago, traveling through expanding space, getting stretched, reddened, diluted. The universe communicates in photons, and those photons arrive with scars. Our task is to read those scars and translate them into a cosmic speed limit. But translation is fragile. You must know how bright something truly is before you can use its apparent brightness to infer distance. You must know the intrinsic properties of a signal before you can use it as a yardstick. And on the scale of billions of light years, any uncertainty is amplified until it becomes a different universe. That is why the tension is so unsettling. Because the two approaches are completely different. They do not share the same assumptions. They do not share the same calibration chains. They do not even look at the same epoch of reality. One method listens to the infant universe to a fossil imprint left when the cosmos was still a hot plasma, before atoms, before stars, before galaxies had time to exist. The other method measures the universe we see now with exploding stars, rotating galaxies, and distance ladders built step by step through the local cosmos. They are like two witnesses to the same event, separated by 13 billion years, giving incompatible testimonies. And if both are honest, then the universe is the liar. That is the nightmare at the heart of this. Not that we made a mistake, but that our best model is incomplete in a way that only reveals itself when you compare the beginning to the end. When you ask the universe a question twice, and it answers differently depending on when you listen. In the next part, we will go to the oldest light we can see, not to learn history, to interrogate a relic, because the cosmic microwave background is not just a picture of the early universe. It is a set of numbers encoded into temperature fluctuations so subtle they feel like whispers. And those whispers predict an expansion rate, a number that should match what we measure today, but it doesn't. And that discrepancy is not just a measurement problem. It might be the universe telling us it has another rule, a hidden ingredient, a missing term in the equation that governs everything you have ever known. And it has been there the entire time, expanding silently while we pretended the story was finished. If you want to know how fast the universe is expanding today, it seems almost absurd to begin by staring at the universe as it was nearly 14 billion years ago. But that is exactly what we do, because the earliest light we can see is not just old, it is structured. It is a fossil imprint of physics at a time when the cosmos was not a landscape of galaxies, but an ocean of heat so intense that atoms could not hold together, a charged fog of protons and electrons, a plasma where light could not travel freely because every photon was constantly scattering, bouncing, trapped. For hundreds of thousands of years, the universe was like that. Not dark, not empty, not quiet. A blinding, humming, dense atmosphere of radiation and matter coupled together so tightly they behaved like one fluid. In that fluid, pressure and gravity fought a continuous war. Gravity tried to pull matter inward, forming wells. Radiation pressure pushed outward, resisting collapse. And the result was sound. Not sound the way you know it. Not vibrations in air, but compressions and rarefactions in the primordial plasma. Acoustic waves traveling through a universe that had not yet learned how to be transparent. Those waves mattered because they drew patterns. They carved a characteristic scale into the cosmos, like ripples freezing into ice. Then, roughly 380,000 years after the beginning, something changed. The universe cooled just enough for electrons to bind with protons to form neutral hydrogen. The charged fog thinned. Photons stopped scattering so often, light decoupled from matter and suddenly had permission to fly. The universe became transparent, and the radiation that had been trapped for almost 400,000 years was released in every direction at once. That released light is still here. It has been traveling ever since, expanding, with space stretching to longer wavelengths, cooling from a searing glow to a faint microwave whisper. It fills the entire sky, even in places where there are no stars, no galaxies, nothing at all. The cosmic microwave background, CMB. If you could see microwaves with your eyes, the sky would not be black. It would be a uniform dim glow in every direction, the after-image of a time when the universe was young enough to fit inside a single breath. But it is not perfectly uniform. If it were perfectly smooth, we would have nothing to work with. Instead, it contains tiny fluctuations in temperature differences of only tens of microkelvin patterns, so subtle they feel like the universe was trying to hide them. Those patterns are everything. They are the fingerprint of the early cosmos, the imprint of those primordial acoustic waves, and the initial seeds of structure that would later become galaxies and clusters. And here is the crucial point. The CMB does not directly tell us Hexero. It tells us something deeper. It tells us the geometry and composition of the universe at that early time, and it reveals a specific physical scale, the sound horizon. The sound horizon is the maximum distance those acoustic waves could have traveled before the universe became transparent. A cosmic ruler defined not by human construction, but by the speed of sound in the primordial plasma and the time available before decoupling. It is a length scale imprinted into the sky. You can see it in the angular size of the CMB's fluctuation patterns, like a repeating motif. And because we understand the physics of that early plasma with extreme confidence, we can calculate the sound horizon in absolute terms in megaparsecs by using known particle physics and general relativity. Then we compare that physical scale to what we observe in the sky. This is where the universe becomes an equation. The angle tells you the ratio between a known physical size and the distance to the surface of last scattering the shell of space from which the CMB photons last bounced. That distance depends on how space has expanded over cosmic time, and that expansion history depends on the energy content of the universe, radiation matter, and dark energy. This is the engine room of modern cosmology. From the CMB's pattern alone, we can infer the density of matter, the density of dark matter, the fraction of baryons, the tilt of the primordial fluctuations, even whether space is curved. And once you lock those in, the model predicts how fast the universe must be expanding today. It predicts H0, a value, a very specific value. When satellites like WMAP and Planck measured the CMB with astonishing precision, they did not just see a blurry relic. They extracted a cosmological parameter set so tight it feels almost claustrophobic. And in that set, H0 lands around 67 kilometers per second per megaparsec. Give or take a fraction, not a guess, a prediction, a number produced by fitting the early universe's fingerprint to the standard model ΛCDM. If you believe the model, that number should match what we measure in the late universe, because the universe cannot have two expansion rates at once. It cannot have one H0 encoded in its baby picture and another written across its modern face. Unless something is wrong, this is where the tension begins to feel like an accusation. Because the CMB result is not just an isolated measurement, it is entangled with the entire early universe framework. If you change H0 in the CMB analysis, you do not just shift one number. You have to change the cosmic composition. You have to change the sound horizon. You have to change the balance of radiation and matter. You have to rewrite the conditions under which the first structures could form. The CMB is like a locked vault. You can open it, but only if you know the correct combination of physical laws. And within those laws, the combination yields a specific H0. So when late universe measurements insist on a higher value, the question becomes sharper. Either the CMB interpretation is wrong because ΛCDM is missing something, or the late universe distance ladder is wrong because our cosmic rulers are flawed, or something in the universe evolved between then and now, something that changed the expansion history without leaving an obvious trace, a hidden ingredient that briefly altered the rhythm of reality. Because the CMB does not merely look back, it reaches forward. It predicts the present, and right now, the present is refusing to cooperate. In the next part, we will step away from the relic sky and into the nearby cosmos, where we build distances the hard way, rung by rung, using light as a ladder across the void. We will see why late universe measurements are so direct, so persuasive, and so dangerous. Because they do not infer H0 from a model. They measure it, and they keep getting a different answer. To measure the expansion of the universe, you need two things. You need distance, and you need speed. Speed is the easier part because the universe stamps it onto light. When a galaxy is moving away, the wavelengths of its light stretch as they travel through expanding space. The spectrum shifts toward red. The farther the galaxy, the faster it recedes and the stronger the redshift. This is not a subtle effect. It is clean physics. It is measurable. Redshift gives you recession velocity, but distance is where the universe becomes cruel. Because distance is not written directly into the photon. A photon arrives with a color, a direction, and an intensity. The color tells you how much space has expanded while it traveled. The intensity only tells you how bright it appears. But apparent brightness is not distance unless you already know the true brightness at the source. And that is the trap. To turn apparent brightness into distance, you need something with a known intrinsic luminosity, a cosmic light bulb with a fixed wattage. If you know how bright it truly is, then you can compare it to how bright it looks from here, and the dimming tells you how far away it is. That is the inverse square law. Brightness falls off with distance squared. The problem is that the universe does not come labeled, so we build labels. We build a ladder. Not a metaphorical ladder, but a literal chain of calibration steps. Each rung depends on the one below it. Each rung extends the reach of the next, and at the top of that ladder sits hetero inferred from the slope of distance versus redshift. This is the cosmic distance ladder, and it is both one of the most ingenious achievements in science and one of the most fragile. The first rung is geometry, parallax. As Earth orbits, the Sun nearby stars shift slightly against the background. The angle is tiny, but with precise measurements, it becomes a distance in pure trigonometry. No assumptions about brightness, no models of stellar behavior, just geometry. Parallax anchors everything, but parallax only reaches so far. Beyond a few thousand light years, the angles become too small, even for our best instruments. So we climb to the second rung. We use objects whose brightness varies in a predictable way, objects that can be calibrated using parallax in the nearby universe, and then used as standard candles farther out. One of the most important is the Cepheid variable, a star that pulses. Its brightness rises and falls in a regular rhythm, and the period of that pulsation is tightly linked to its intrinsic luminosity. Longer period means brighter star. Once you calibrate that relation using Cepheids close enough for parallax, you can look at Cepheids in other galaxies, measure their periods, and infer their true brightness. Now you have distance to those galaxies. Now the ladder reaches beyond the local neighborhood, but the universe is vast. Even Cepheids fade beyond a certain range, so we climb again. We move to an even brighter standard candle. Type Ia supernovae. These are catastrophic explosions, the thermonuclear destruction of a white dwarf pushed over a critical limit. They are so bright, they can outshine entire galaxies for a brief moment, visible across billions of light years. And crucially, they are not random. Type Ia supernovae have a characteristic light curve, a pattern of brightening and fading. That pattern correlates with their peak luminosity. With calibration, you can standardize them. You can turn them into beacons. The ladder works like this. Parallax calibrates Cepheids. Cepheids calibrate distances to galaxies that host Type Ia supernovae. Those supernovae, now calibrated, become standard candles that reach deep into the smooth expansion of the universe. Then you plot recession velocity from redshift against distance from the ladder. The slope of that relation is hetero. This method is direct in a way that feels almost surgical. It does not require reconstructing the entire early universe history. It does not require assuming ΛCDM. It measures the late universe as it is, and for years it has been refined with ruthless care. Astronomers hunt for Cepheids with clean environments, measure them with consistent instruments, correct for dust, for metallicity, for selection effects, for every bias that might distort their brightness. They cross-check with alternative calibrators, like the tip of the red giant branch, another standard candle method that avoids some Cepheid systematics. They compare multiple supernova samples. They test for hidden correlations that could skew the slope. And even after all that, the ladder returns an answer. Not 67, more like 73 kilometers per second per megaparsec. That difference sounds small until you translate it into the scale it controls. At 73, the universe is younger. At 67, it is older. At 73, the early growth of structure must be slightly different. At 67, the late time acceleration has a different balance. These are not aesthetic disagreements. They are different universes. And here is the real reason this feels like cosmic horror. Because if the ladder is wrong, it must be wrong in a way that survived scrutiny at every rung. A hidden bias that slipped through geometry variable stars and exploding thermonuclear events without leaving an obvious footprint. That is possible, but it is a tall order. And if the ladder is right, then the CMB inference is wrong, meaning the early universe framework is missing something. But the CMB is also tied to multiple independent pieces of evidence, like baryon acoustic oscillations, another relic of those primordial sound waves seen later in the clustering of galaxies. The early universe hangs together. The late universe hangs together. but they do not hang together with each other. That is the tension. Not a disagreement between sloppy measurements, a disagreement between two internally consistent stories. So when you stand in the middle, holding both truths, you start to feel the floor tilt. Because in physics, when two precise methods disagree, you do not merely update a number. You search for the assumption that both methods share without noticing. You ask what invisible thing could shift both interpretations. You ask what rule could change between epochs. And that is where the word baseline becomes sinister. Because Hezero is not just the expansion rate, it is the calibration of cosmic distance itself. If that calibration is unstable, if reality's ruler is warped, then every inference we make about the universe is perched on a trembling scale. In the next part, we will climb to the brightest rung and stare directly at the supernovae, the late universe beacons that insist the cosmos is expanding faster than it should. And we will see why this disagreement refuses to die. Because the ladder is not a single experiment. It is a machine built to crush doubt. And yet, it keeps delivering the same unsettling answer. There is something almost obscene about using an explosion as a measuring stick. A star dies violently, and we turn its last light into a ruler. But the universe is so vast, and our reach is so small that we accept whatever reliable beacons it offers. Type Ia supernovae are among the brightest. When they ignite, they do not just announce themselves to their host galaxy, they announce themselves across intergalactic emptiness. For a few weeks, a single point of light can rival the combined glow of hundreds of billions of stars. Then it fades, leaving behind an expanding shell of debris, and the silence returns. If you want to map the expansion of the universe, these are the flares you use. Because a supernova is more than brightness. It is a pattern. A type Ia supernova follows a characteristic light curve. It rises, reaches a peak, and declines. And the shape of that curve correlates with the peak luminosity. The broader the light curve, the brighter the explosion. That relationship is what allows standardization. A raw type Ia is not a perfect candle. It has scatter. But when you correct its peak brightness using its light curve shape and color, it becomes a standardized candle with remarkably low dispersion. Low enough to measure distances far beyond the local universe. Low enough to build a Hubble diagram distance versus redshift for hundreds, then thousands of supernovae. And that diagram is not just a plot. It is the universe's expansion, written in points of light. Here is the core idea. If you know how bright a supernova truly is, then the dimming you observe tells you how far away it is. If you also measure the redshift of its host galaxy, you know how fast space has expanded since that light was emitted. When you do this for many supernovae at relatively low redshift, where the relationship is close to linear, the slope of distance versus recession velocity gives you H0, a present-day rate inferred from nearby cosmic space. The supernovae themselves do not provide the absolute scale. They need calibration. They need a distance anchor. That is why the lower rungs of the ladder matter so much. Cepheids, or the tip of the red giant branch, provide distances to galaxies that have hosted type Ia supernovae. Those distances set the true luminosity of the supernovae. Once you know that you can use standardized type Ia explosions to extend distances outward, this is where the tension becomes stubborn. Because when teams build this ladder carefully, the result comes back with a higher H0 than the CMB predicts. Not once, not by accident, repeatedly. It is tempting to blame the fireworks. To say supernovae must not be as standard as we think. Maybe their progenitors differ, maybe their environments matter, maybe dust dims them unpredictably, maybe metallicity shifts their brightness, maybe selection bias means we preferentially detect brighter ones farther away. All of those are real concerns. And the supernova community has spent years interrogating each one. They divide samples by host galaxy type. They examine correlations with star formation rates and galaxy mass. They correct for dust extinction using color information. They calibrate photometry across instruments, across surveys, across decades. They simulate selection effects to see if the observed distributions can be skewed into a false slope. They compare different standardization methods. And still, the higher H0 remains, which is why the phrase, "two precise measurements disagree," is almost too mild. It is more like this. One method reads the universe's infant fingerprint and says the expansion rate should be slow enough to yield a certain cosmic age and a certain sound horizon scale. The other method lights up the nearby universe with exploding stars and says, no, the expansion is faster and the distances line up that way consistently. Both methods are not just measuring H0, they are measuring the structure of reality that generates H0. So the real question is not who made an error. The real question is what assumption is hiding beneath both stories. Because every rung of the distance ladder has the same vulnerability. It assumes light behaves the way we think it does in the environments we are using, that intrinsic luminosities are stable after correction, that the calibration is not warped by subtle astrophysics, that the universe is not playing tricks with our candles. But if the problem is not in our candles, then the candles are revealing something darker, something about time, because the late universe method is local and direct, and the early universe method is inferential and global. If both are right, then the expansion history between the early universe and now must be different from what ΛCDM assumes. And that means something changed, not in a gradual, gentle way, in a way that shifts the inferred sound horizon or the late-time distances enough to reconcile these values, which is like saying the universe has an extra beat in its rhythm, an extra pressure, an extra species. An extra component that appears, alters the tempo, and vanishes, or a modification of gravity that behaves one way at early times and another way now, or a field that wakes up briefly and changes the expansion rate without breaking everything else. This is why the tension feels like a doorway, because H0 is not just a parameter. It is a constraint. You cannot change it without paying a price somewhere else in the age of the universe, in the growth of structure, in the clustering of galaxies, in the shape of the CMB peaks. So if the supernovae are insisting on a faster expansion, then the universe must compensate. And compensation means physics. It means hidden terms. It means that the baseline of reality, the model we use to translate light into truth, is missing an ingredient. The fear is not that our measuring sticks are flawed. The fear is that our measuring sticks are working perfectly, and they are pointing to a universe that does not match the rules we believed were complete. In the next part, we will place the two numbers side by side and do the thing physics hates most. We will accept that both could be precise. And then we will ask what happens when two true measurements cannot both be true, because that is the moment the tension turns into a fracture. Put the two numbers on the same page, and the problem stops feeling academic. From the early universe, from the cosmic microwave background, CMB interpreted through ΛCDM, the expansion rate today lands near 67 kilometers per second per megaparsec. From the late universe, built from a distance ladder of geometry variable stars and type Ia supernovae, the expansion rate lands near 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec, a difference that sounds like a rounding error until you realize what a megaparsec is. A megaparsec is about 3 million light years. So that 6 is added again and again and again, over distances so large your mind cannot hold them. It becomes a different age of the universe, a different expansion history, a different growth of cosmic structure, a different set of invisible balances between matter, radiation, and dark energy. And worse, it is not fading as the data improves. It is sharpening. In science, disagreement is normal. It is how errors are found. But there is a particular kind of disagreement that feels like a warning when independent methods become more precise and still refuse to converge. That is what makes Hubble tension unsettling, because these are not two sloppy estimates. They are two clocks. One clock is buried in the first light of the universe, in the pattern of primordial sound waves frozen into temperature fluctuations. It is a clock made of physics so early and so hot that it feels closer to fundamental law than to astronomy. The other clock is built from the modern cosmos, from the brightness of pulsating stars and the last flare of dying white dwarfs. It is a clock made of direct observation of photons, gathered by mirrors and detectors calibrated with ruthless repetition. Both are meant to be measuring the same present. That is the contradiction. You can forgive a disagreement when methods share assumptions. A shared bias can infect both. But these methods live on opposite ends of cosmic time. They use different data, different systematics, different pipelines, different failure modes. If they disagree, something has to give. Either the early universe inference is wrong because the model that connects the CMB to today is incomplete, or the late universe ladder is wrong because one of its rungs is subtly warped, or the most unnerving option, both are right within their own domains because the universe changed in a way our baseline model does not allow. This is why the tension is not just a debate about a parameter, it is a stress test of coherence. ΛCDM is supposed to be the bridge between the early universe and the late universe. It takes the blueprint of the CMB and projects it forward. It says, given this composition, given this curvature, given these initial fluctuations, this is how the universe must expand and evolve. If the bridge predicts 0 to be 67 but the late universe measures 73, then the bridge is missing a beam, or the late universe is lying. But if the late universe is lying, it must be lying in a very specific way. Because the ladder is not just one measurement, it is a chain, each rung cross-checked, each correction audited, each systematic hunted like a hidden predator in the data. For the ladder to be wrong, the error must survive parallax geometry, survive stellar physics, survive supernova, standardization, survive dust corrections, survive selection, bias modeling, survive instrument calibration. It is possible, but the universe is forcing us to entertain a disturbing thought. The error would have to be elegant. It would have to be precisely tuned to shift H0 upward without destroying the internal consistency of the ladder. On the other side, for the CMB inference to be wrong, the problem is not a simple mistake in reading the map. It would mean the early universe contains something we have not accounted for, something that changes the sound, horizon scale, or the expansion history between then and now. Because H0 does not float alone. In the CMB, it is entangled with other parameters, like a knot. Change one string and the whole configuration shifts. The height and spacing of the CMB acoustic peaks, the matter density, the baryon fraction, the damping tail, the lensing signal, they all conspire to lock the solution into a narrow corridor. So when late universe measurements demand a different H0, the universe is not offering an easy compromise. It is offering a choice. Either we discover a hidden systematic that has evaded the best scrutiny we can apply, or we accept that our standard model is not the whole story. And if it is not the whole story, then Hubble tension is not an inconvenience. It is evidence, a sign that the universe has an extra dial, a new field that briefly dominated early expansion and then faded into invisibility. A new relativistic species, dark radiation, adding pressure in the young universe. A subtle modification of gravity that changes how space-time responds across cosmic time. A rule that only reveals itself when you demand that the beginning and the end agree. This is where the cosmic horror lives, not in a monster, in a mismatch, in the possibility that reality has been giving us a consistent narrative only because we have not been asking the question sharply enough. Because a universe that cannot agree with itself is not just mysterious, it is unstable in the way certainty is unstable. It means the laws we use are not the laws that fully exist. They are approximations that work until precision becomes unforgiving. In the next part, we will step into the heart of ΛCDM itself, not as a textbook model, but as the invisible architecture that holds our cosmic story together. Because to understand why the tension is terrifying, you must understand what it threatens to break. We have a story of the universe that is so successful it almost feels dangerous. It explains the afterglow of the first light. It explains how galaxies cluster into filaments and walls and voids so large they make entire clusters look like dust. It explains why the universe is mostly hydrogen and helium. It explains why distant supernovae appear dimmer than they should, revealing an accelerated expansion that no one expected. It explains why the cosmos is nearly flat, why its structure grew the way it did, why the statistical pattern in the cosmic microwave background looks like a set of notes played by the same instrument across the sky. And it does all of that with a small handful of ingredients. A cold, invisible matter that does not shine and does not collide the way ordinary matter does. but weighs down space-time and pulls on galaxies like a ghost gravity. A dark energy component represented by a constant lambda that acts like a pressure built into the vacuum stretching space itself. And then ordinary matter radiation, neutrinos, and initial fluctuations seeded in the earliest moments. This story has a name that sounds like code because it is, in a sense, a set of equations compressed into a label. ΛCDM. Lambda for dark energy. CDM for cold dark matter. It is the standard cosmological model. And like any model, it is not the universe itself. It is a map. But it has been such a good map that we built our sense of reality on it. So when Hubble tension appears, it is not merely a mismatch between two measurements. It is a mismatch between two claims the map makes about the territory. To see why, you have to understand what lambda CDM is really doing. It is not just a list of components. It is a timeline. It takes the early universe, a hot and dense plasma, and evolves it forward under general relativity and known particle physics. It describes how the universe cools, how radiation gives way to matter, how matter gives way to dark energy. It describes how tiny initial fluctuations grow under gravity into larger structures, and how the expansion rate controls that growth by deciding how much time gravity has to work before space pulls things apart. In this model, H0 is not a free-floating knob you can turn without consequence. 0 is the final tempo of a symphony that was set by its opening notes. The first notes are encoded in the CMB, the spacing of acoustic peaks, the scale of the sound horizon, the ratio of baryons to dark matter, the tilt of primordial fluctuations. These early conditions, when fed into the model's equations, produce a predicted expansion history. From that expansion history, you get a present-day H0. So when the CMB implies 67, it is not because the CMB directly measures H0 with a ruler. It is because the CMB measures the early parameters and lambda CDM evolves them forward, and the evolved universe arrives at 67. This is why the tension threatens the model, because the late universe, with supernovae and distance ladders, is measuring H0 more directly, and it is arriving at a higher value. If you force lambda CDM to accept that higher value, it must adjust other parameters to compensate. But those parameters are already tightly constrained by the CMB itself, and by other evidence, like baryon acoustic oscillations, and by the way large-scale structure grows. The model is like a machine with gears that interlock. Turn one gear, and the others must move. Hubble tension is what you see when the gears refuse to mesh. And yet, lambda CDM is not fragile in the usual way. It has survived countless tests. You can measure the relative heights of the CMB peaks, and it predicts the baryon fraction. You can measure the clustering of galaxies, and it predicts how matter should distribute. You can measure gravitational lensing, and it predicts the subtle distortions. You can measure the abundance of light elements, and it matches what the early universe should synthesize. So the model is not obviously wrong. It is wrong only in one place, a place that might be the key to everything. That is why cosmologists keep circling this discrepancy like predators around a wound. Because historically, when a model works everywhere except one corner, that corner is where new physics hides. Not always, but often enough to be feared. Sometimes the corner collapses into a systematic error, a mundane flaw, but sometimes it opens, and behind it is a deeper rule. Here, the deeper rule would have to do something specific. It would have to change the relationship between the early universe and the late universe without destroying the rest of the model's success. It would have to change the inferred sound horizon scale, or the expansion history at intermediate times, or the way gravity behaves in a way that shifts the derived H0. And it would have to do it quietly, because the universe does not look like it is on fire. The CMB is still there, coherent and precise. Large-scale structure still forms. Galaxies still cluster. The model still works beautifully in most places. So if there is missing physics, it is missing in a subtle way. A field that briefly mattered and then hid. A particle that behaves like radiation early on, then becomes irrelevant. A modification to gravity that only reveals itself on cosmic scales. Or something even stranger, a small difference in how we interpret distance, not because our instruments fail, but because space-time itself is trickier than our assumptions. This is the moment when the universe starts to feel like a locked-room mystery. We have a body, the discrepancy. We have suspects, systematics, and new physics. We have a timeline early and late. And we have evidence that seems airtight on both ends. So we do what detectives do. We revisit the obvious. We try to eliminate the mundane. We hunt the ghost in the instrument. Because before you rewrite reality, you have to be sure you did not misread a ruler. In the next part, we go after the most human possibility, systematic error. Not as an insult to the measurements, but as a necessary ritual. Because if Hubble tension survives the hunt for systematics, then the universe is not merely confusing. It is telling us that our model is incomplete. And that is when cosmic horror stops being a mood and becomes an implication. Before you accuse the universe of hiding new physics, you have to do something humiliating. You have to assume the problem is you. That's somewhere in your pipeline, somewhere between the photon and the plot, a bias slipped in. Not a dramatic mistake. A small one, the kind of error that survives because it looks like reality. That is what a systematic is. A systematic is not randomness. Randomness averages out as you gather more data. A systematic is a direction, a drift, a subtle tilt in the measurement that does not go away with more observations. It becomes sharper, more confident, more wrong. If Hubble tension is a systematic, then it is a ghost embedded in the instrument or in the calibration, or in the assumptions we do not notice we are making. This is why the tension is so difficult, because both sides have different ghosts. Start with the distance ladder. Its power comes from being direct. Its weakness comes from being layered. Every rung is an opportunity for distortion. At the bottom, parallax seems clean, but even geometry has traps. The motion of Earth, the wobble of the spacecraft, the way detectors map pixels into angles, the way crowded star fields can blend multiple sources into one brighter point. If you overestimate brightness, you underestimate distance, and a small bias in nearby distances can ripple upward until it becomes a different expansion rate. Then come Cepheids. Cepheid variables are living clocks of plasma and gravity, and their period luminosity relation is one of the great gifts of astrophysics. But Cepheids are not identical. Their metallicity, their chemical composition, can affect their brightness. The dust in their host galaxies can redden and dim their light. Crowding can blend them with neighboring stars, making them look brighter than they truly are. Every one of those effects can shift distances, not by much, but enough. And above Cepheids come type Ia supernovae standardized by their light curves. Again, not identical. Their environments matter. Their progenitors might differ. The dust in host galaxies can vary. The selection effects of surveys can favor brighter events at larger distances, subtly skewing the slope. And all of it depends on photometric calibration. The universe does not hand you brightness. It hands you counts on a detector. To turn counts into brightness, you need calibration of instrument response, filter transmissions, detector sensitivity, and cross-survey consistency. One small mismatch between systems can become an artificial tension. That is the ladder's vulnerability. Its strength is also its weakness. It is an engineered chain. Now look at the early universe side. The cosmic microwave background seems almost inhumanly precise, but it also requires interpretation. You do not directly measure H0 from the CMB. You measure an angular scale, the pattern of acoustic peaks, and infer physical scales using a model. So, systematics here can hide in assumptions about foregrounds, instrument beams, calibration of the detectors, and the subtraction of emissions from our own galaxy. But more importantly, there is a deeper kind of systematic on the CMB side model dependence. If ΛCDM is missing a component, then the inference of H0 is biased not because the data is wrong, but because the model used to interpret it is incomplete. In that sense, new physics and systematic error can blur into each other. A missing term in the equation behaves like a systematic shift in a derived parameter. So the cosmologist's job becomes a kind of ritual purification. They try to kill every mundane explanation first. They recalibrate. They test alternative distance anchors, like the tip of the red giant branch, which relies on a different stellar population than Cepheids. They measure Cepheids in different filters to reduce dust sensitivity. They run blind analyses to avoid subconscious tuning. They model selection effects and see if they can fake the tension. They compare independent supernova surveys. They build entirely different pipelines and see if the answer changes. And on the early universe side, they test different CMB datasets, different foreground treatments, different assumptions about neutrino masses, helium abundance, recombination physics. What has emerged from this effort is not complete consensus, but it is a kind of resilience. The tension has survived enough cross-checks that it no longer feels like a simple ghost. The ladder's calibrations have been challenged and refined repeatedly. The CMB inference has been tested and remains stable within its framework, and yet the numbers remain separated, which leads to the most unsettling possibility that what we are calling a systematic might be something deeper, because if you look at the distance ladder from a certain angle, it is a test of the assumption that the universe's candles are stable across environments and cosmic time. If you look at the CMB inference from a certain angle, it is a test of the assumption that the cosmic recipe is complete. If either assumption fails, you can call it a systematic, or you can call it new physics. Either way, the universe changes. This is where the cosmic horror grows teeth. Because it is one thing to find an error in a telescope, it is another thing to find an error in the laws you use to interpret the universe's oldest light. If the tension is real, then the universe has been holding back a piece of itself, not in a dramatic way, in a subtle way that only appears when you demand consistency across 13 billion years. And consistency is not optional in physics. It is the foundation, so the hunt continues. If we cannot blame the ladder and we cannot dismiss the CMB, then we need another witness, another method, one that does not depend on the same calibration chains, one that sees the cosmos through a different kind of lens. In the next part, we will use gravity itself as an instrument. We will let massive galaxies bend space-time into a clock, because light does not just travel through space. It travels through geometry, and geometry can delay it. Those delays can become distances, and those distances can become a new measurement of Hatzero, a measurement that might break the tie, or confirm that the universe is expanding wrong. When you cannot trust your ladders, you turn to something that cannot be fooled by brightness. You turn to gravity. Gravity does not care how luminous a star is, or how dusty a galaxy is, or how well you calibrated your detector. Gravity only cares about mass and geometry. And on cosmic scales, mass and geometry can do something extraordinary. They can bend light. General relativity says that a massive object warps spacetime, and light follows the curves of that warped geometry. When a distant quasar or galaxy lies behind a massive foreground galaxy, the foreground mass acts like a lens. It can split the background light into multiple images stretched into arcs mirrored across the sky. It is beautiful, but it is also useful. Because those multiple images are not identical in time, light taking different paths through a warped space-time does not arrive simultaneously. One path may be longer. One may pass deeper through the gravitational potential, experiencing a larger relativistic delay. So the universe produces a delay, a time difference between images of the same object. And time delays can be measured. If the background source is variable, like a quasar whose brightness flickers, you can watch those flickers echo between the multiple images. A brightening occurs in one image, then later appears in another like a cosmic stutter. The delay might be days, weeks, sometimes months, and those delays encode a distance scale, not a distance to a star, a distance to space-time itself. In lensing time delay cosmography, the measured delays depend on the mass distribution of the lens and on a specific combination of angular diameter distances between observer lens and source, and that combination scales inversely with H0. Higher H0 means smaller distances, which changes the delay. Lower H0 means larger distances, which changes the delay. So by measuring the time delays and modeling the lens mass distribution carefully, you can infer H0. This method does not use Cepheids. It does not use supernova standardization. It does not use the cosmic microwave background. It uses geometry, time, and gravity, which is why it became so important. Because if lensing yields a value close to the late universe ladder, it suggests the tension is not a ladder error. If it yields a value close to the CMB, it suggests the local distance ladder might be biased. And if it yields something else entirely, the universe is even stranger than we thought. So, what does it say? It tends to land closer to the higher expansion rate. Not as high as every ladder result, not always with the same confidence, but consistently leaning away from the CMB value. That is not a final verdict. Lensing has its own ghosts. The mass distribution of the lens galaxy must be modeled, and that modeling can be subtly wrong. There can be mass along the line of sight that contributes extra lensing. There are degeneracies like the mass sheet degeneracy, where different mass profiles can produce similar lensing configurations while shifting inferred distances. But the method is independent enough that its preference matters. It adds weight to the idea that the late universe is not simply miscalibrated. It suggests that the higher H0 may be real, and if the higher H0 is real, then the early universe inference is pointing to missing physics. This is where the story becomes unsettlingly consistent, in the wrong way. Not consistent with the standard model, consistent with the idea that the standard model is incomplete. Because now you have a ladder telling you one thing, a lensing clock telling you something similar, and an early universe relic predicting something lower. 3 witnesses, 2 align, 1 stands apart, and the one standing apart is not random. It is anchored in the earliest light in a universe we thought we understood with pristine clarity. There is another kind of dread here. Lensing does not just measure H0. It forces you to confront the fact that space-time itself is the medium of the measurement. You are not measuring expansion in a separate stage. The stage is the measurement. The geometry delays the light, bends it, duplicates it, and in doing so reveals the scale of distances. Which means, if new physics exists, it may not be a tweak to a single number. It may be a different behavior of geometry over cosmic time, a different relationship between matter and curvature, a subtle evolution in the way gravity acts across billions of years. Hubble tension becomes not only a discrepancy, it becomes a suspicion that gravity has been performing a consistent illusion. And if that is true, then the universe is not just expanding. It is evolving in its rules, but we still need more evidence. Because lensing, for all its elegance, requires careful modeling of masses we cannot see fully. So cosmologists sought another method that is even more direct, one that measures distance without relying on brightness at all, a method that turns the universe into a resonating instrument, a method that uses ripples in spacetime itself as a ruler. In the next part, we will listen for gravitational waves, and we will see how collisions of dense objects can become standard sirens, a distance scale written not in light, but in the amplitude of spacetime's own trembling. And if those sirens speak clearly, they may tell us whether the universe's expansion rate is truly wrong, or whether we have simply been misreading its light. There is a way to measure cosmic distance that does not care how bright an object is. It does not care about dust. It does not care about metallicity. It does not care about calibration ladders built from fragile rungs of astrophysical behavior. It cares about something more fundamental, the shape of a signal predicted by general relativity, a gravitational wave. When two massive compact objects spiral into each other, they disturb spacetime itself. They generate ripples that propagate outward at the speed of light, stretching and squeezing space as they pass. For a moment, the universe carries a vibration, and if you can detect that vibration, you can read a distance directly from it. This is why gravitational waves are so important to the Hubble tension story, because they offer a new kind of measurement, standard sirens. A supernova is a standard candle because you infer distance from brightness. A gravitational wave event is a standard siren because you infer distance from amplitude and waveform. The waveform tells you the intrinsic strength of the event in a way that depends on the masses and spins of the merging objects. The amplitude you detect here on Earth falls off with distance again by a geometric relationship. If you know what kind of system created the signal, the waveform encodes how loud the siren truly was. And the loudness you measure tells you how far away it is. This is distance without a ladder, distance from geometry and relativity. In principle, it is a clean path to Hak zero. But there is a catch, because Hasro requires not only distance but recession velocity. You need a redshift. Gravitational waves alone do not directly provide redshift in the same way light does. So to turn a standard siren into a cosmological measurement, you need to identify the host galaxy of the event, or at least statistically associate it with a population of galaxies, and measure redshift from light. The cleanest case is when a gravitational wave merger also produces an electromagnetic counterpart, a flash or afterglow that allows telescopes to locate it precisely in the sky. Then you have distance from the gravitational wave. You have redshift from the host galaxy, and you can plot a point on the Hubble diagram. This happened. A neutron star merger created a gravitational wave signal, and it also produced light. Astronomers chased the afterglow and found the host galaxy. For the first time, the universe offered a distance measurement built from space-time itself, anchored to a redshift. The result was not razor precise because the uncertainties were large, but it proved the method. And more events followed. Black hole mergers, neutron star mergers, mixed systems. Most of them have no clear light counterpart, but even without a counterpart, you can still do cosmology statistically by using galaxy catalogs. If the event could have occurred in any of many galaxies within the sky localization region, you can weight the possibilities and infer a distribution of Hak zero. It is not clean in practice yet, but it is independent. And independence is what we need. This is why standard sirens feel like the universe giving us a third way to interrogate it. Because Hubble tension is fundamentally a disagreement between early and late, a third path can act like an impartial witness. If standard sirens eventually converge on the higher H0, then the universe is truly expanding faster than the early universe blueprint predicts. If they converge on the lower H0, then the distance ladder might be biased. If they converge somewhere unexpected, then we have not even understood the shape of the problem. Right now, the sirens are still faint in their verdict. The uncertainties are wide. The sample sizes are small, but the trajectory matters. With each detection, the error bars shrink. With each improved detector, run the sky localizations tighten. With each better galaxy catalog, the statistical association becomes less ambiguous. This is not a single experiment. It is a growing listening network. And in that growth is a kind of dread, because if the sirens eventually agree with the ladder and lensing, then the case for new physics strengthens. It becomes harder to dismiss the tension as a ghost of calibration. It becomes a persistent feature of reality, a signature, a clue. But even if standard sirens become decisive, they will not by themselves tell us what the missing physics is. They will only tell us that something is missing. Hubble tension is not just about which number is right. It is about why. Why would the early universe encode a lower expansion rate than the late universe measures directly? To answer that, we have to ask what could alter the early universe inference without destroying the rest of the standard model's success. That is where the potential suspects begin to look like cosmic horror, not because they are fantastical, because they are subtle, because they are exactly the kind of thing that could have shaped the universe invisibly and then stepped back into shadow. In the next part, we will explore one of the most haunting possibilities that the early universe had extra light in it, extra relativistic energy, an unseen radiation component that changes the sound horizon and shifts the inferred zero, an addition so small you would never notice it in daily life. But on the scale of the cosmos, it would rewrite the tempo of everything, and it would mean the universe was never as simple as our model pretended. If the cosmic microwave background is a fossil, then Hubble tension is a discrepancy carved into the fossil's ruler. The ruler is the sound horizon. The maximum distance primordial pressure waves could travel through the early universe before the cosmos became transparent and let light escape. That sound horizon is a physical scale, a length, a standard etched into the sky. And the CMB does not measure it directly with tape. It infers it. It infers it from the physics of a young universe filled with radiation and matter. expanding, cooling, ringing like a struck bell. Now imagine this. What if the bell was ringing in a room we miscounted? What if the early universe had more radiation than we think? Not light you could see, not starlight, relativistic energy, particles moving near the speed of light, a background that contributes pressure and expansion without leaving a simple signature in the late universe. Cosmologists call this possibility extra relativistic degrees of freedom, often compressed into a parameter called NF. NF is in spirit a head count, a way of asking how many light species were present in the early universe contributing to its energy density like neutrinos do. In the standard picture, you have photons and you have neutrinos, three families of them faint and almost untouchable. But if you add anything else that behaves like radiation, early on NF increases. Dark radiation, a sterile neutrino, an axion-like particle, anything that free streams and adds pressure while the universe is still young and hot. Why does that matter for Hubble tension? Because extra radiation speeds up the early expansion. In the radiation-dominated era, the expansion rate is tied directly to how much radiation exists. More radiation means a faster expansion. A faster expansion means less time for sound waves to travel before the universe becomes transparent. Less time means a smaller sound horizon. And this is where the trick happens. The CMB measures the angular size of that sound horizon in the sky. It sees a pattern of peaks and troughs at specific angles. If the physical sound horizon was smaller but the angle stayed the same, then the distance to the surface of last scattering must also be smaller. Smaller distance in an expanding universe typically implies a higher H0 when you evolve the model forward. So the chain is simple and terrifying. Add extra early radiation. Shrink the sound horizon. Keep the observed angular scale. Force the inferred distances down. Push the derived H0 up. Suddenly, the early universe can be reconciled with the late universe without accusing the distance ladder of error. This is why extra light is one of the first doors people try. It is elegant. It is minimal. It changes the early tempo without necessarily wrecking the late-time cosmic structure. But the universe is not generous, because the early universe is not observed only through the CMB peaks. It is also constrained by other relics. BBN, Big Bang nucleosynthesis, the formation of light elements when the universe was minutes old, depends on the expansion rate then. Speed it up too much, and you change the predicted abundances of helium and deuterium. The CMB's damping tail, the fine-scale smoothing of fluctuations, is sensitive to the same physics. And BAO, baryon acoustic oscillations, are the late-time echo of that same sound horizon imprinted into the clustering of galaxies. If you shrink the sound horizon, the BAO scale shifts and the late universe pushes back. So extra radiation cannot be arbitrary. It must be tuned, enough to shift H0, not enough to violate the tight web of constraints that already exist. This is where the cosmic horror deepens. Because if the solution requires a delicately balanced extra component, it implies the universe has hidden parameters that can be adjusted while leaving most of reality looking normal. A universe that can hide an entire particle species in its earliest moments, then bury its evidence inside statistical patterns, is not a universe that wants to be fully known. And there is another unsettling implication. If dark radiation exists, then the early universe was not just a hot plasma plus a few neutrinos. It was a richer ecosystem of fields and particles, many of which may have faded, decayed, or become invisible to our detectors. Not because they are far away, because they are everywhere and still unreachable. So, the question becomes sharper. Is Hubble tension telling us that the early universe had extra light? Or is it telling us something even stranger, that the universe did not simply have more radiation, but that something briefly changed the rules of expansion itself, like a field that surged and then vanished, leaving only a mismatch between the beginning and the end? In the next part, we will walk into that possibility, a component that is not present all the time, a kind of early dark energy that wakes up, alters the cosmic pace for a brief epoch, and then disappears into the background. If it exists, it would mean the universe's baseline is not constant. It is conditional, And that is a much more frightening kind of reality. Extra radiation is one way to change the early universe's tempo, but it is also blunt. Radiation leaves fingerprints in too many places. Push it too far, and the universe protests through nucleosynthesis, through the fine structure of the cosmic microwave background, through the late-time echo of baryon acoustic oscillations. So cosmologists began to imagine something subtler, something that behaves like a ghost, not a permanent ingredient, a temporary one. A component that turns on, nudges the expansion history, and then fades so completely that the late universe hardly remembers it existed. This idea is often gathered under a phrase that feels almost too simple: early dark energy. If dark energy today is the mysterious pressure that accelerates expansion, then early dark energy is a version of that pressure that mattered briefly in the young universe at just the right time and then became negligible. It is not the same as adding more matter. It is not the same as adding more radiation. It is adding an extra push in the cosmic dynamics for a specific epoch. A correction term that wakes up, changes the scale of the sound horizon, and then steps back into silence. The motivation is surgical. The CMB's angular pattern is exquisitely measured. It tells us the angle of the sound horizon at last scattering. The late universe tells us a higher has-zero. To reconcile them, you want the physical sound horizon to be smaller than the standard model predicts, so that the same observed angle implies a shorter distance and therefore a higher has-zero when evolved forward. Early dark energy can do that. If the universe expanded a bit faster just before recombination, then sound waves had less time to propagate. The sound horizon shrinks, the inferred zero rises. But unlike adding dark radiation, early dark energy can be designed to fade away quickly, so it does not permanently alter the later expansion the way extra radiation does. In many constructions, it is a scalar field, a kind of energy stored in a field, value behaving like potential energy at first. Then, as the universe expands and conditions change, the field begins to roll or oscillate, and its energy density dilutes faster than matter, sometimes faster than radiation, becoming irrelevant by the time the universe is a few percent of its set current age. It is a burst, a pulse, a brief additional pressure that changes the universe's rhythm at a critical moment, then disappears. This is where the horror enters, because a field like that is not a tweak to a known ingredient. It is a new degree of freedom in reality. A new thing that exists not as a particle you can point to, but as a background component that alters the expansion of space itself. It would mean the universe is not governed by a fixed set of rules that apply uniformly across time. It is governed by a set of rules that can evolve, that can activate, that can hide. And early dark energy is attractive precisely because it hides well. It can increase has-zero inferred from the CMB without ruining the standard model's success everywhere else, at least in some parameter ranges. But the universe does not give you a free knob. Early dark energy affects more than the sound horizon. It can shift the shape of the CMB power spectrum. It can alter the growth of structure. It can change how matter clusters on certain scales. And it must do all of this while still matching the exquisite precision of CMB data and the web of large-scale structure constraints. So, the question becomes not just, can early dark energy solve Hubble tension? The question becomes, can it do so without leaving a trail? Because if a field briefly dominated the energy budget of the universe and then vanished, the cosmos would have been shaped by something that no longer exists in any obvious way. That is a deeply unsettling thought. It is like discovering that the architecture of your world was determined by a force that has since been erased, leaving only a small discrepancy in the corners of the blueprint. You can feel its influence, but you cannot touch it. You can infer it, but you cannot see it directly. And that is what makes this kind of solution feel like cosmic horror rather than simple model adjustment. It implies reality has hidden episodes. Moments when the universe was governed by an extra term in the equation, a silent regime change that left no monument except a mismatch in a number we expected to be unique. There is another layer to this. If a scalar field exists to solve Hubble tension, it likely does not exist only for that purpose. Fields tend to come with consequences, couplings, interactions, potential landscapes, instabilities. A field that can wake up and fade away suggests an underlying theory with many possible states, many possible histories. And our universe is just one trajectory through that landscape. Not necessarily the simplest, not necessarily the only one. If that is true, then Hubble tension is not merely a measurement problem. It is a sign that our cosmic history includes a chapter we have not read. A chapter written in a language we barely understand: fields, potentials, and early universe dynamics. In the next part, we will step even closer to the edge. Because early dark energy assumes the equations of gravity remain the same, and we are only adding new components to the cosmic energy budget. But there is another possibility, that gravity itself, the relationship between matter and curvature, is not constant across cosmic time, that the universe is not merely missing an ingredient, it is running on a different set of rules. And if gravity can evolve, then the baseline of reality is not a baseline at all. It is a moving floor. There is a reason cosmologists hesitate before saying the words modified gravity, because gravity is not just another force in the list. Gravity is the rule that decides what a distance even means. It is the geometry that tells light how to travel, matter how to fall, and time how to pass. When you change gravity, you are not adjusting a parameter. You are editing the stage while the play is still running. And yet Hubble tension pushes us toward that edge. Because if the early universe's blueprint and the late universe's measurement cannot be reconciled by hidden errors, then either we are missing a component or we are missing a rule. ΛCDM assumes general relativity is correct on cosmic scales. It assumes that matter and energy curve spacetime in a specific way, and that this curvature governs the expansion history through the Friedmann equations. It assumes the same gravity applies when the universe is a hot plasma and when it is a cold web of galaxies. But what if that is the assumption that breaks? What if the relationship between energy and expansion is slightly different at different times? What if gravity is not a fixed constant in the background of reality, but an effective behavior that can evolve? In that case, the tension is not telling you the universe has an extra ingredient. It is telling you the universe has a different grammar. One of the simplest ways this idea appears is through extra fields that couple to gravity. A scalar field, for example, can modify the way curvature responds to matter, effectively changing the strength of gravity over time or over scale. In these theories, general relativity becomes an approximation, a limit that emerges when the field is quiet, when its influence is screened, when the universe is in a regime where the old equations happen to work. But in other regimes, the field participates, and the cosmic expansion evolves differently. Here is why this matters for Hubble tension. The early universe inference of H0 depends on a chain of assumptions that connect the CMB's angular pattern to physical distances. Those distances depend on how fast the universe expanded at different epochs. If gravity behaved differently around recombination, the time when the CMB was released, then the inferred sound horizon and the mapping from angles to distances could shift. You could reconcile a lower inferred H0 from the CMB with a higher measured H0 in the late universe by changing the cosmic expansion history in a way that does not require adding permanent new energy components. Instead, you change the rule that translates energy density into expansion rate. This is a seductive option because it targets the bridge between early and late directly. But it is also terrifying because gravity is everywhere. A change in gravity does not stay politely confined to one measurement. It changes how structures grow. It changes how galaxies cluster. It changes how gravitational lensing bends light. It changes how BAO appears in the distribution of matter. It changes the statistical texture of the universe. So any modified gravity explanation has to thread a needle. It must alter the expansion history enough to shift H0, but not so much that it breaks everything else we observe. And everything else we observe is a lot. Large-scale structure is not a vague picture. It is a precision measurement. The cosmic web carries information about how gravity amplified tiny primordial fluctuations into galaxies and clusters. Weak gravitational lensing measures the integrated mass distribution by the distortions it causes in background galaxies. Redshift space distortions measure how matter flows under gravity, and the CMB itself is lensed by intervening mass, leaving a subtle imprint in its higher-order statistics. Gravity cannot be changed without leaving fingerprints in all of these places. That is why modified gravity theories often come with something called screening, a mechanism that hides the modification in high-density environments so that local tests of gravity in the solar system remain satisfied while cosmic scales behave differently. In other words, the universe would have two faces. Locally, gravity looks like Einstein's. Cosmologically, it is slightly different. That is not a comforting thought. It suggests the laws we trust most are not universal laws, but context-dependent behaviors. And context dependence is exactly what Hubble tension feels like. The universe answers differently depending on when and how you ask. But even beyond screening, there is a deeper discomfort. Because modified gravity implies that what we call dark energy might not be an energy component at all. It might be the effect of gravity deviating from general relativity on large scales, making expansion accelerate, not because the vacuum has pressure, but because the equations themselves change. If that were true, then lambda, the term we treat as a constant of nature, would be a placeholder for our ignorance, a label we use to cover a gap, and Hubble tension would become another symptom of that gap, a sign that the placeholder is failing. This is why psychologically Hubble tension is so powerful. It tempts us into rewriting the deepest layer of the model, the layer that tells space-time how to behave. Because if you can change that layer, you can move Hg zero without necessarily inventing a new particle species. But the price is enormous. You trade a missing ingredient for a missing foundation. You trade a universe with hidden matter for a universe with hidden rules. And hidden rules mean the cosmos is not fully described by the equations we can write down today. It is described by a deeper framework that only looks like our physics in the regimes we have tested most thoroughly. A universe like that is not just larger than us, it is more secretive than us. In the next part, we step back from specific suspects and look at the broader implication. If the tension persists, then whether the cause is a new field, a new particle, or a modified gravity law, the same conclusion keeps returning. Our baseline is incomplete. And when the baseline is incomplete, every distance you thought you understood becomes provisional. Even the meaning of far becomes something the universe can renegotiate. There is a comforting assumption buried inside almost every cosmological measurement, that the universe is the same kind of universe everywhere, that a distance is a distance, that a ruler once calibrated remains a ruler, that the equations you use to translate photons into truth do not change their meaning between epochs. Hubble tension is what happens when that comfort begins to rot, because at its core, the tension is not just a disagreement between two experiments. It is a disagreement about what the universe considers scale. The early universe gives us a scale through the sound horizon, a physical length imprinted into the cosmic microwave background. The late universe gives us a scale through calibrated candles and geometry distances built rung by rung through the nearby cosmos. If those scales disagree when translated into Hazaro, then one of them is wrong. Or more frighteningly, the translation itself is wrong. This is where the idea of a miscalibrated baseline becomes more than a metaphor. In ΛCDM, the baseline is the relationship between energy content and expansion, and the relationship between early universe physics and late universe observables. We treat it like a finished machine. Insert CMB parameters, output the universe. But what if the machine is missing a gear? Not a gear that obviously breaks everything. A gear that only matters when you demand that the earliest ruler and the latest ruler agree. That missing gear could be a new field, a new particle species, a subtle interaction in the dark sector, a time-varying behavior that changes the expansion history and the sound horizon without leaving a loud signature anywhere else. The reason this feels so unsettling is because it implies the universe has hidden parameters. If the standard model needs extra ingredients to reconcile her zero, then reality has more degrees of freedom than our current story admits. It means there are things that can exist in the universe and influence its growth while remaining nearly invisible to our usual methods of detection. Not because they are rare, because they are woven into the expansion itself. Think about what that means. You can live inside a universe whose dominant components are unseen, whose acceleration is driven by something we cannot touch, and whose early history may have included fields or particles that shaped everything and then vanished from our perception. And the only reason we notice is because two numbers fail to match, a mismatch in a parameter that most people have never heard of. That is the kind of horror that belongs to cosmic scales, not an event, a realization. A realization that the map is not only incomplete, but that it can be incomplete in a way that looks complete until you measure finely enough. Because this is what precision does in cosmology. It does not merely refine the picture, it interrogates the assumptions. Hubble Tension is an interrogation, and the universe is not answering the way we expected. Now consider another layer. What if the late universe ladder is not wrong in its methods but wrong in its premise? What if the standard in standard candle is only approximately standard, and the approximation subtly changes with environment, with chemical composition, with the age of stellar populations? Not enough to ruin supernova cosmology. Not enough to obviously contradict data, but enough to bias zero. In that case, the baseline is miscalibrated, not because physics is missing, but because astrophysics is complex. A mundane explanation dressed in cosmic consequences. But even that mundane explanation is unsettling, because it means the universe's measuring tools are not stable objects. They are living systems with hidden dependencies, and the only way to know is to keep measuring and keep discovering new corrections, like peeling layers of uncertainty off a fruit that never ends. Either way, the baseline is not secure, and this insecurity spreads because Hazro is used to infer many other things. It affects the inferred sizes and ages of cosmic structures. It affects the calibration of distances to galaxy surveys. It affects the mapping between redshift and distance that underlies large-scale structure studies. When Hazro is uncertain, the entire cosmic coordinate system becomes slightly unsteady. It is like building a cathedral on a foundation that you assumed was bedrock, only to learn it is slowly drifting. Not collapsing, drifting, just enough that if you return after enough time, the geometry does not match your memory. This is why cosmologists care so much. Not because they want a clean number for its own sake, but because a stable baseline is what allows cosmology to be a science of inference rather than a collection of disconnected observations. If the baseline can be wrong, then the universe is not just hard to measure, it is hard to know, and that leads to the deeper dread. If new physics is needed, it will not just fix Hazero, it will open a new sector of reality. A set of interactions or fields that could have shaped the early cosmos that might still shape the late cosmos, and that we have not yet learned how to detect directly. Hubble tension would be the first crack, not the last. Because once you accept that the standard model is incomplete, you must accept that there may be other discrepancies waiting, hidden behind the limits of our current precision. A universe with hidden parameters is not a universe that reveals itself willingly. It reveals itself under pressure, one mismatch at a time. In the next part, we will stop treating this as a technical dispute and confront the implication head-on. What does it mean for our understanding of reality if two precise measurements cannot both be true? Not just for cosmology, for our idea of laws, for our belief that the universe is coherent. Because if the cosmos can disagree with itself, then certainty is not a property of the world. It is a temporary illusion produced by imperfect measurement. On a quiet day, the universe seems stable. The stars hold their positions. The laws of physics feel immutable. Space feels like an empty stage, indifferent but consistent. Hubble tension is a reminder that this feeling is not evidence. It is comfort. Because the tension forces a question that sounds philosophical but is brutally technical. Is the universe fully described by the rules we currently use to predict it? Or have we mistaken a successful approximation for the final truth? A parameter mismatch would be easy to dismiss if it were isolated. But Hubble tension is not isolated in its implications. 0 is one of the numbers that anchors the entire cosmological coordinate system. It tells you how to translate redshift into distance, how to convert the pattern of the cosmic microwave background into a physical scale, how to infer ages, sizes, and growth rates across cosmic time. If zero is uncertain, the universe becomes slightly out of focus. But if He0 is split into two values depending on method, the universe becomes something worse. It becomes inconsistent. And inconsistency is poison to a model, because models do not fail all at once. They fail where they are least tested. They fail where a hidden degree of freedom has room to hide. That is what hidden parameters means in this context. It means there are additional knobs in the universe that can be turned without immediately breaking the rest of the picture. A new field that contributes briefly. A new particle species that acts like radiation early then becomes irrelevant. A subtle interaction within the dark sector between dark matter and dark energy, changing the expansion history in a way that mimics a shift in Hubble. A modification to gravity that emerges only on the largest scales. These are not fantasies. They are the natural kinds of extensions you get when you admit that our model may be incomplete. And that admission has an existential edge, because it means the universe can contain structure we cannot directly observe, not just in the sense of distant galaxies, but in the sense of rules and components that do not announce themselves, except through their influence on expansion. The universe would be larger than our maps in a deeper way, not more galaxies, more law. And once you accept that, you begin to see the tension as a warning about certainty itself. We have gotten used to the idea that physics is finished in its foundations, that we have the basic equations and only need to solve them in detail. But Hubble tension suggests that the basic equations might still be missing a term, missing a regime, missing a relationship that only becomes obvious when you compare the earliest light to the latest distances. This is megalophobia in mathematical form, a fear not of a large object but of a large possibility space. The idea that there are many consistent universes permitted by deeper physics and that our observed universe is one point in that landscape. And the only reason we have not noticed the rest of the landscape is because our measurements have not been sharp enough to expose the contour lines. There is also a specific terror in the way the universe forces the issue. It does not give us an anomaly in a place we can ignore. It gives us an anomaly in a place that touches everything. Because expansion is not a side story. Expansion is the background against which all cosmic evolution occurs. It is the breathing of space-time. If the breathing rate is not what we thought, then everything that depends on timing and distance is affected. The age of the universe, the formation rate of galaxies, the growth of clusters, the mapping of matter distribution, even the calibration of other cosmological probes. And that means a resolution to Hubble tension, whatever it is, will not be a patch. It will be a redefinition of the baseline. Either we discover a hidden systematic and refine our measurement tools, which is still a kind of redefinition because it changes how we translate light into distance, or we discover new physics, which is a redefinition of reality itself. In both cases, the universe becomes less simple, and that is the part that should unsettle you, because simplicity is not guaranteed. It is an aesthetic preference. Nature owes us nothing. It is entirely possible that the universe contains layers of fields and interactions that only matter in narrow windows of time, shaping cosmic evolution, like invisible hands and then withdrawing. It is entirely possible that our current standard model is like a shadow cast on a wall sharp enough to guide us, but not the object itself. Hubble tension is the moment you notice the shadow's edge does not align with the object you thought it came from. In the next and final part, we will return to the central contradiction with a colder gaze. Two measurements, both precise, both defensible, both unable to coexist. And we will ask what physics always asks when faced with that kind of impossibility. Which assumption must die? Because the universe will not allow two truths to occupy the same space. If both are true, then truth is not what we thought it was. And if one is false, then finding the reason will reveal something the universe has been hiding, either in our instruments or in its own rules. Either way, the ending is not comforting, it is clarifying. And clarity at cosmic scale can be the most frightening thing of all. At the end of all of this, the universe offers you a simple, brutal choice. Two numbers, two answers. Two stories about the same reality. and they do not match. The early universe, through the cosmic microwave background, CMB, interpreted by ΛCDM, says the expansion rate today is lower near 67 kilometers per second per megaparsec. The late universe through distance ladders and the light of type Ia supernovae says the expansion rate today is higher near 73. Gravity through time delay lenses has leaned toward the higher value. Space-time, through gravitational wave sirens, is building a third witness that will eventually speak with more authority. And still the contradiction remains. In a coherent universe, two true measurements of the same quantity must converge. If they do not, then one of the following must be true. One measurement is wrong, haunted by an undiscovered systematic that has survived every reasonable attempt to exorcise it. Or the standard model that connects the early universe to the late universe is incomplete. Or the quantity we are trying to measure is not as simple as we thought because the universe's behavior changes across time in a way that makes a single number an oversimplification. These are not equally comfortable. The first option is the one we always hope for because it keeps reality stable. It says the universe is fine and we misread it. But even that is not fully comforting here because the systematics would have to be unusually subtle. They would have to hide inside the calibration of distance, inside the behavior of stars, inside the selection of supernova samples, inside the translation between detector counts and brightness. They would have to shift hetero while leaving the rest of the ladder's internal consistency intact, a ghost with perfect manners. The second option is the one that makes cosmologists restless in the way you become restless when you sense a floorboard is loose. Because ΛCDM has been the narrative spine of modern cosmology. It has held together an enormous amount of evidence with a small set of parameters. If it is missing something, then we have been living inside a model that looks complete, only because we have not demanded coherence at the highest precision. And what could be missing is not necessarily something dramatic. It might be a new particle species dark radiation that altered the early expansion rate. It might be an early dark energy field that briefly dominated and then faded into silence. It might be an interaction in the dark sector that changes the evolution of structures. It might be a modification to gravity that emerges on the largest scales. Any of these would mean the universe has additional degrees of freedom, hidden parameters, extra dials, and the presence of extra dials changes how you think about knowledge. Because it means nature can hide components in narrow epochs of time, shaping reality and then withdrawing, leaving only a statistical residue in the sky. It means the universe is not merely large, it is layered. The third option is the strangest, but it is the one that feels most like cosmic horror when you sit with it long enough. That the disagreement is not an error and not a missing ingredient, but a sign that the concept of a single H0 may be incomplete. Because H0 is not a constant in the deepest sense. It is the expansion rate today, inferred under assumptions about how the universe behaves. If the behavior changes, if expansion history includes hidden transitions, if space-time responds differently under different conditions, then trying to compress the universe into one stable baseline number may be the wrong language. In that case, the tension is not merely a dispute, it is the universe refusing to be summarized. So what happens next? The measurements get better, parallax becomes more precise, Cepheid calibrations improve, alternative anchors mature, supernova samples expand and become cleaner, time delay lensing gathers more systems, gravitational wave detectors listen longer and deeper, building a catalogue of standard sirens that will either converge on one value or reveal a more complex truth. And as this happens, one of two things will occur. Either the tension will soften and the two numbers will finally meet and the universe will return to coherence under the standard model, or the tension will harden into certainty. If it hardens, then Hubble tension stops being a problem. It becomes evidence. Evidence that the universe contains something we have not accounted for. Evidence that the cosmic story has an extra chapter. Evidence that the baseline we used to define reality was missing a term. There is an emotional consequence to that evidence, because we want the universe to be fully legible. We want the early light, and late distances to tell the same story to form a single narrative that closes cleanly. But the universe is not obligated to be narratively satisfying. It is obligated only to be itself. And if it is itself, in a way that includes hidden fields, hidden particles, or evolving rules, then the tension is not an annoyance. It is the first time we have caught reality disagreeing with our description of it. That is the moment science becomes something more than measurement. It becomes confrontation. A confrontation with the possibility that our most successful model is not the final map, that the cosmos is operating with more complexity than our current equations can express, and that we only noticed because two methods staring into opposite ends of time refuse to agree on a single number. A universe that expands wrong is not necessarily a universe that is broken. It may be a universe that is deeper than we thought. And depth at cosmic scale is what creates the true feeling of megalophobia, not the sight of something large. The realization that the rules beneath everything might be larger than your mind can contain. Hubble tension is the crack. What comes through that crack will define the next story we tell about reality.